video. Hopefully we can have a conversation between all of us, I guess. Archana, I don't know if it'll
yeah, it will. And then what I will do is I will read off the questions that we have received so far and for whom the questions are, and then maybe we can take them one at a time and we can address them. So
yes, yeah, and to a certain extent, I'd like to get the debate going amongst. We've got some interesting mix of views here, so it'd be good to stimulate that. So hopefully the questions can stimulate that as well.
Okay. So the first question is for Steve Roberts. Would like to know if Steve has looked at the SSE push eventing / telemetry streaming support in Redfish.
No, not in any detail. I think I've heard of it, and we were looking to adopt that as a next generation item. So I think it's off on our radar screen, but I haven't dug into it to understand the specification.
Okay.
So
that was by Jeff Otter, and I think he's with HPE. And another gentleman also commented on that and said, kind of interested too. Both event service and telemetry service are in advanced development stages in OpenBMC. What software were used in presented OpenBMC telemetry solution on the BMC side? And then I think there were a few comments back and forth from other people on OpenBMC plus REST API plus WebSockets to push out events to the BMC. I think I'm speaking in a foreign tongue, so.
Okay, I need to get onto the NV chat thing. Maybe we can these guys, and if it does draw some interest, maybe we could bring it into Alan's call.
Okay. The other question was also to you again. Did you try to pull BMC instead of pushing DAT form? I'm assuming that from the BMC. I'm wondering what is more efficient.
We found that the push was more efficient just because what was interesting was when we loaded the data generator up to start to take the measurements, what we found was that the processor temperature and power were the first things to fluctuate. And that fluctuation happened on I think that sensor was reading at a 20 millisecond interval or something. And so, you could definitely not, we had to constrain that push, but the one-way traffic of the push was just more efficient. So we, and we didn't need and then we ended up using a WebSockets API from Perl, which would keep the stream open. And between that combination, not having to deal with the authentication. So we did some experimentation, I guess, is the bottom line, and the sequence of the pull was a lot less inefficient than the push.
One more question, and this was just to all of the presenters. I know Phil addressed it in the text, it's in the chat itself, but they're looking for some recommendations from the presenters about backup / hold up time typically needed for HPC nodes and the latency needs. This drives the battery proximity and runtime needs, which occupy space in the system. So maybe
I'll just double down.
Can address it.
I'll just double down on what Phil covered. Most large HPC systems, think about multi-megawatt systems, are not put on UPSs because it's just too much money. So some of them in the commercial space will have A and B feeds, but most actually large HPC systems don't even have that. And ultimately, people do the math that if power is reliable enough, they get more bang for the buck, and taking the money they would spend for a large UPS system and buying more nodes than actually just flooring a big UPS system to back it up.
Yeah, I would agree with that. And you'll just roll back to the last checkpoint whenever you come back with power. Yeah. I will say where I have seen UPS, it's more of a holdover in order to get generators back online, and usually that's only like a second or that order of magnitude. So if there is a need for that, that's probably your it's sized by your generator power uptime.
And it's really
or
important.
even your storage system. Sometimes people will put storage
Yes.
nodes on the UPS.
Yeah, good point.
Right, but
That's actually really important. That's
Yeah.
where I was going with that. The compute kind of goes away, and you restart from the previous checkpoint, but the storage cannot go off abruptly, because then you're in corruption hell with a parallel file system. So the storage is typically on UPSs.
Yeah, you've got to commit everything you've got. Yeah.
So those are the only questions that I have here. Alan, I'm going to let you lead now.
Okay, no, that was an interesting little side conversation for sure. It's actually just one popped to my head, guys. As we go more and more data centric, you know, the memory, everything's sort of going in memory, and storage is becoming persistent memory. And so, you know, we traditionally think of the storage is over there and the compute is over here. But in reality, if you look at exabytes, it takes longer to load the data than it does to run the job if you go forward with that combination. So you really need it all squidged together somehow. Can you make any comments on that, or am I just misseeing the future here?
I would be happy to comment on that. Most of my experience in the last few years has been AI based rather than traditional HPC. It's a lot happening in that space. But yeah, having the storage with close affinity to the training, it's actually the other way around. People are putting AI training wherever their storage is, because if you think about it, the data sets tend to be large. You know, we've seen data sets, training sets that are in the petabytes, and you will make multiple epoch traversals of that data set across multiple nodes. So you think the data set might be being served to, you know, pick your number, 500 nodes concurrently, like all parallel streams, and you're going to traverse that petabyte data set maybe you know, several hundred times for a training run. You know, it just really wants to be very close.
Right.
Otherwise, it's unmanageable.
I'll double down on that. We've done roofline plots between traditional simulation HPC workloads and kind of different training, different machine learning models, and it's almost an order of magnitude the kind of IO bandwidth required for some of those compared to traditional simulation HPC that really sets kind of basic initial conditions, then runs. It's different though if you look at kind of the new workloads that are coming in, like I was talking about it, with massive data being ingested from large instruments. But in this case, what you want to have is kind of a multi-tier data hierarchy, where you're going to have at the edge some kind of a storage system that will be able to do the pre-processing and everything, but then that flows up to or elsewhere to where supercomputers or other compute capabilities are at. But definitely the era where we had a very kind of compartmentalized parallel file system like Lustre or GPFS that kind of sat on the side of big compute, I think is coming to an end. And the fact that we're moving data mostly through POSIX interfaces and HPC and like MPI for while the job is running, also that is moving to an end. I think we're going to a place where it's going to be load stores and a lot more PGAS and a lot different kind of runtime environments. And that's a good thing, because I think that applies more broadly to more workloads, probably more easily than the kind of the forced way of learning the parallel file systems and MPI that we've been.
Nicholas, I think you touched on a couple of good points there, and Rob, in terms of so we've got these memory fabrics moving towards load store memory type operations. When we've seen a lot going on in that over the last few years with Gen Z, CXL, OpenCAPI, C6, etc. And I think you also talked, in my words, you talked about distributed computing. You push the compute to the edge where the data is. You do some pre-processing and you only bring the intelligent data in. So I guess my question, you know, what that starts to bring us to is are we looking at a world where the supercomputer isn't just a bunch of racks in the cloud, or it is, part of it is, but it's also got edge machines as well. So it's distributed around the world. You know, for traditional weather modeling, I'm not a weather modeling expert, but that's a classic HPC type problem. you know, you've got weather monitors, millions of them, billions of them, probably all over the world. If you're monitoring them in real time, would you make your weather supercomputer a completely distributed one, obviously with big data centers as well, you know, but pulling that real-time data in from the weather and actually distributing the compute around that sort of, I guess that's a low data problem, relatively speaking, but well, not when you aggregate it all up. So yeah, I guess the question is, well, there's two questions. How are we going to normalize these fabrics? Is CXL the answer for all memory attach? You know, when we go to distributed compute, should we be looking at all of that geographically spread stuff as the high performance computer, or instead of just in this one machine in the data center?
So let me start by answering your second answer first. There will still be massive supercomputers for the next decade and maybe beyond that, just for the capability. The weather example you just used is a key one, actually. You need to have that core capability of a large system because those models are very big. That's why we're building exascale system, right? Exascale systems are going to be able to run climate models with a degree of precision we've never been able to do before. And the reason for that is just because of the sheer size of those systems. So that's why, we'll, in my opinion, we'll keep building those large supercomputers. But they're part, that's what we call kind of horizontal federation. They're part of an ecosystem that feeds in from the edge, and then that propagates the data out to the cloud. And so they're not isolated so much. So the capability needs to remain, and there's a lot of needs for that.
Right.
And then on the interconnect, and I really want the other panelists to chime in on that. I think CXL carries a lot of the interesting features. For instance, HP has been strong promoter of Gen Z. We see Gen Z is kind of morphed in with CXL. It has a lot of the load store capabilities we're looking for. And the reason for that also is that if you look at some of the new silicon that's coming in machine learning, some of them are not even running a full OS stack and they're non-bond. I mean, so what they want to do is they're not running a full POSIX file system. So they want to be able to do load stores elsewhere in the system to get the data and then send it out, because they don't have the capability to do the full file open and close. So so I think, yeah, having an interconnect that can support that, and that CXL definitely at the node, the rack level. Beyond that, we need to think about how we expand that beyond that.
Okay. Any other comments?
Yeah. I think that the current versions of CXL have limitations, but I think that you know, the standard is working on addressing those. You know, moving towards CXL3. The question is always going to stay there. You know, what sort of access bandwidth and, you know, random access latency and bandwidth is required for a specific use case, and depending on the use case, that's CXL will be wildly efficient, or it will be insufficient. So you know, there will continue to be some sort of hierarchy or stratification. I mean, for example, pooled memory is really important. Today, you can go to Google Cloud and you can rent one of their brand new instances that's 16 GPUs and VLink connected, and that pooled memory HBM2 resource between those GPUs is about 600 gigabytes. So more than half a terabyte of unbelievably high bandwidth, globally accessible memory. And you can see that's going to continue to be an important model, especially for accelerators.
Any other comments, Ivan or Steve?
Yeah, I would tend to agree that, like, you know, we definitely need more alignment and pursue the existing work at the CXL level. But yeah, moving forward, there might be a need to kind of optimize and have maybe fabrics that are a bit smarter to redirect optimally, like, you know, the traffic where it should be going. And I think it's going to be part of the, like, you know, the efficiency discussion, right? As we move towards, like, you know, more and more power, how do we start making these systems a bit more efficient? as we're trying to move the data faster and to lower latencies, right? So how do we start having maybe a more, as the quantity of memory is also increasing based on latency and the actual storage, how do we start optimizing like also the level of storage closer to the load, but also like, you know, on the storage to make sure that we're not going to be losing that data. And I totally agree that, like, you know, from an exascale perspective, currently the models are, you know, so huge that it becomes difficult. But on the memory storage, we're also like, you know, catching up. So at some point, like even, you know, from a GPU or accelerator perspective, the quantity of memory at the HBM is increasing ever, but for sure for the exascale, I think we're still going to require, like, you know, data centers with that amount of computing power.
Alan, I think that when we get to that, we're going to have some large innovation here, and I hope that innovation could be adopted, you know, up to PCI Gen 6, and we keep the velocity. I think that will give CXL standard enough time to catch up and deal with some of the things that the HPC community understands was weak. And I know there's proposals in there to fix that. But if we, you know, at Gen 6, the speeds are so wire limited, I think the industry is going to probably take a pause there. If we can make sure that the OCP, you know, accelerator board interfaces can keep up with that velocity and you know, intersect at that level, I think we'll do better than we have before about creating these standard interfaces that other people can play and these innovations can contribute into.
Okay, thanks. That's good. I'd like to switch gears now, and Rob, actually, I want to pick up on one thing that you mentioned about the modularity, and we're at too fine a grain at the OEM level. Absolutely, you know, obviously you guys at a silicon level are innovating at a hell of a rate of knots, and I you know, I can't imagine that we can keep up. But I think that demarcation line of where can OCP contribute, and where do we suddenly break it and say, well, we've got to leave it to the experts in the various silicon domains is a critical question. And my question to you is, what I love about the OEM is we've suddenly had an explosion of processor companies. I'm sure it'll narrow back down again, you know, after this explosion for sure, and there'll only be a few left standing. But in a heterogeneous world where we're at right now, at least for the next decade, I would say, you know, the high performance compute, the domain specific architects would like to pick and choose a bit of GPU, a bit of FPGA, a bit of AI, a bit of CPU. And so one thing is, forgotten the chap's name, the Penguin Computing guy, Phil. Phil. And I forgot. Oh no, yeah. Somebody mentioned the ratio of processors to. So that was Ivan.
Yeah.
The processors. Yeah, processors to accelerators. I think of them all as peer processors, and everybody has SoCs on board now. So why can't we bring the processors into an OAM module? And if OAM is too granular, Rob, how am I, as a system architect, going to be able to pick and choose my favorite heterogeneous pieces to make the best domain-specific solution for my particular HPC problem?
Wow, fantastic question. A couple of things. So first, I've been doing processor and system architecture for more than 30 years, a lot more than 30 years. And this is a unique time where I think we are reintegrating, re-verticalizing, and you know, I talked about density. I think the density actually comes down to communication bandwidth, and that I think you're going to see tighter and tighter integration of all of these elements. They will be architected as a whole. And I'm not sure you're actually going to have a viable option to pick and choose pieces. Or maybe put another way, it may not be a very wise choice, because you'll probably get radically suboptimal capability. So that's just my opinion.
Well, I guess on that point, for domain specific versus generic, which are all data centers right now tend to be very generic. But if you really do go domain specific, then maybe you are limiting for other applications. Is that what you're saying?
That's possible. But for example, if you take so I agree with your thesis that it's all part of computing, right? There is no such thing as a CPU separate from an accelerator. I think we're getting to heterogeneous computing as a norm. And so in that sort of world, if you choose a CPU that wasn't designed to go with this accelerator, for example, it's probably not going to work that well, and the software stack is certainly not going to be tuned, and that may in fact be more important than anything else. That's really my point. I think we're going to see. I think it is the new computing model. I mean, that's why I got into this space, because it was the biggest shift I had seen in my career. And I think that this is the new normal. And that's true at the edge as well. You're going to see these heterogeneous computing elements at the edge all over the place as well. So it's, mini-me's sprinkled all over the place.
Exactly.
Going back to the OAM module, it's actually a very nice module. It's a very nice spec. But depending on architectural decisions you might make, for example, trying to tightly integrate a CPU with an accelerator, or some way you might want to build some inter-module communication for specific, architecture, it can be extraordinarily confining as well, right? It may not allow you to do those things you want to do. And that's really my point, is allow somebody to use OAM if they want, but also allow them to build a system level architecture that they believe is an advancement in architectural science. Allow them to integrate whatever sort of communication protocol they need to or want to, instead of being confining. And I think OCP could, for example, provide innovation domain like enclosures, for example. Here's all the important key points, with power, cooling, data feed. Here's where things come in and out. Go do what you want inside of that box.
Right.
Do you think that
Rob?
Yep.
Rob, as you know, OAM specification was the starting point.
Yeah.
But immediately after that, the teams got together and created OAI, the Open Accelerator Infrastructure. So within that infrastructure, since it is a modular design, there are a number of input-output delineations that different modules can be built. Immediately after OAM, we have the universal baseboard, universal building block, the UBB. The flexibility that you're looking for is, of course, present. The design can be done at the UBB level. So this is the type of things that, as part of this modular building block architecture, we've been promoting, in that if somebody wants to go fast, they can. If somebody wants to rely on other people's work, they can. So we're not necessarily limiting people's innovation. We're trying to enable an ecosystem that things can interoperate well.
Yeah. Hey, C-Mac. I guess there's the one missing piece there is the temporal aspect. I agree to everything you say about OAM, OAI, and UBB. But given that the world changes every 6 months, and that's not rhetoric, that's actually real. For example, the BERT, the time from the BERT neural network was from the paper, the seminal paper, to being in production at multiple hyperscale data centers was less than 6 months. It's just unbelievable. And that changed architectures. So the problem is the temporal aspect. if I wait for something to stabilize and then build based on that, it's probably obsolete.
So
yeah, there is HPC at the bleeding edge, but there's HPC for the rest of us as well, which may be that may be okay to be a fast follower. Possibly.
Yeah, no, that's totally legitimate.
But Alan, let me chime in on that. I think, sorry, man, I think UBB, OAM, and all of that, Siamak is directionally correct. I think that's the right thing we want to do for the industry. But I think it's missing the part around the software, and actually running a coherent domain between accelerators is very complicated from a software piece. Right. So
it is unbelievably, unbelievably complicated.
Yeah, and it's interesting that the processors are all adopting, non-transparent bridging, right, and building that into the hardware now. But that's a far cry, to exchange data that way from QPI type of protocols and these coherent protocols, right? And the software, to maintain global directories or solve coherency with this NTP type of interface. I mean, that's what we're getting ready to do with some of the CXL efforts, but that's everybody looks at that and says, hey, this is kind of the bread and butter of the processor.
The comments you're making are all right on. As you say, the system is very complex and is growing in different directions. So that's basically when we need specifications. That's when we need to reduce the complexity to certain fixed elements. You anchor a particular thing. For example, you say anchor the size of the module. It is one rack or one this big only. Then the next one is power distribution. Well, instead of power distribution in 5 different ways, well, the workloads don't care how power is distributed. Well, fix that. Then the next one is the amount of power used. Okay, so we create flexibility. You have 8 modules of X versus 4 modules of double X or 1 module of 8X. So those are the flexibilities they can create. So structure is not bad. Limiting complexity is not bad, but we don't want to reduce innovation, as you suggest. Yes.
The baseboard, though, like you said, fixes the topology. And there was the one presentation from Molex of using cables to do the cross connect, and why not just double down on that and make the topology completely cabled, even for nearest neighbors?
Why don't we? It is part of the architecture. There are certain topologies that have been prescribed based on highly used topologies. But the flexibility does exist within the UBB. And as Alan suggested, one innovation was just go all the way with cables. That's possible. Somebody else suggested, well, maybe it is a fast follower concept. Okay, so if Alan comes up with a particular topology that's feasible, allow somebody else come up with something else, but a lot of people can use that particular one and go spend time in somewhere else.
Yeah. Hey everybody, I think we're at the limit. It is the coffee break. Fantastic discussion. I've got a bunch more topics I'd love to bring up with you guys. But just to say to everybody, look, we can continue this in our sub project. It's definitely an exciting area. I really enjoyed this session, so thanks guys for helping me out and bringing the expertise.
And if you don't mind, as a plug for our Thursday night discussion, we have a panel discussion with esteemed colleagues here on this topic as well, our OAI track.
Okay, I'll come along.
Yeah, hey, thank you everyone for your time. We are going to have a 10-minute break. Everyone, please come back at 9 a.m. We've got a lot of really good content and we've got, a lot of speakers on standby. In the lobby, you can click in. Facebook is sponsoring coffee. I believe Molex is also sponsoring lunch to like the first, X number of visitors. And then we've got meditation breaks in case you just wanted to chill for a little while and take in the sounds and sights. But yeah, thank you so much. And we'll come back here at 9 a.m.
Thank you.
Thank you. Great group of people.
Thank you.
Take care.